Alright, for those of you who were gone, I wanted to go over a couple of examples here, what we went over on Friday. Again, looking at section 2.2, polynomial functions of higher degree, and yesterday we looked at the leading coefficient test and how to tell the general shape of a polynomial function. But today we want to look at how do we find zeros of a function. And particularly here, we're looking at ones that we can factor. So we'll look a little bit at the reviewing of factoring and then also how that impacts the graph. And then we'll look at some multiplicity of zeros as well to finish off the lesson. Alright, so starting with this example, f of x equals x cubed plus 5x squared minus 6x. Because this is an x cubed, we know there are going to be 3 roots of the equation if we set this equal to 0. And if those roots are real numbers, then we have 3 zeros of the function. So we're going to start by setting this function equal to 0. And then also we are going to look to factor. So you'll see each term here has an x, so we can factor out that as a greatest common factor. And then we have this trinomial, x squared plus 5x minus 6. And that can be factored into 2 binomials, x plus 6 times x minus 1. And from that we can tell that the zeros are 0, -6, and 1. Those are the roots of this equation, and because they're all real roots, we have those 3 zeros. Now, if we were going to sketch the graph of this, what we would start by doing is think about our leading coefficient test. The leading coefficient here is the coefficient of the highest degree term, so the coefficient is 1. Since it's positive, we know that we're going to have an upward general trend from left to right because we have an odd power, an odd degree. It's going to be down on one side, up on the other side, and because it's a positive a, it's going to go from the bottom left towards the top right. Okay? Then we would plot the 3 zeros at -6, 0, and 1, and we end up with a graph that looks something like this. Okay? Now, what we are going to look at on Monday is how to tell how high this would go here and how low this would go. You know, does it just barely go over the x-axis, or does it go much higher than what we have drawn? But you can see here we have the majority of this graph. We've got a good idea of what's going on. And then when we find what's known as the relative max or the local max point here and the local or relative min point here, then we'll be able to get an even better sketch of this graph. Alright, so there's one example. Let's take a look at another one. And here we have one that you'll notice is a cubic again, but it doesn't have a common factor that we can pull out of the entire polynomial. Okay, so what we're going to have to do is factor by grouping. Alright, you see I set it equal to 0 because we're finding the zeros, and I'm going to group the first 2 terms here and factor out whatever the greatest common factor of those 2 terms is, which would be a 3x squared. And then we look at the last 2 terms, and there's a common factor of 4, but if we looked at this, you'll notice when we take out the 3x squared, there's an x minus 4. So I'm going to take the negative out with the 4, and that'll make it a positive x and a minus 4 in the parentheses, because that's really the whole key to factoring by grouping like this. You need to get a binomial, x minus 4 in this case, that's identical in both, because that's your common factor that you're going to pull out, and then what's left over is the 3x squared and the minus 4. That will go in a second set of parentheses. So we can already tell one of our zeros is going to be 4, and then we need to set this equal to 0 and solve it in order to figure out what our other two zeros are. And you can see I do that over here on the right. 3x squared minus 4, x squared would equal 4/3, and that's plus or minus 2 divided by radical 3, which, if we rationalize the denominator, would be 2 radical 3 over 3. And I will say, if you're asked to graph this, you don't need to worry about rationalizing the denominator, because on a graph you're going to get a decimal approximation, which for this I believe is 1.1. So you would just say 1 plus or minus 1.1, and that would go on your graph. Okay. Now, we will be looking at how to find zeros for functions that are harder to factor in the next section. We'll start that on Monday, and we'll look more at that on Tuesday. Now, another thing I want to look at is repeated zeros. Okay, and this is what our book calls a multiplicity. All right, if we have a polynomial function and we have this factor x minus a to the k power, and in the previous examples we just had a set of parentheses and that was it, so it was to the first power. But here we're looking at ones that have a higher power, like an x minus 3 quantity squared or cubed. But that yields a repeated zero of x equals a of multiplicity k. All right, and then there are two cases here. One, if k is odd, the graph crosses the x-axis at x equals a. However, if k is even, the graph touches the x-axis but does not cross the x-axis at x equals a. Now let's start by looking at two cases that we're familiar with, and that'll make more sense, I believe, than just reading the words here. So let's look at f of x equals x squared and f of x equals x cubed. We have a quadratic, but if you were to find the zeros, you would get 0 as a root twice, okay, giving it 0 as a 0 with a multiplicity of 2. Okay, here 0 would be your 0, but it would have a multiplicity of 3. Okay, and you guys already know, because these are parent functions, that the graphs are going to look like this. So you see, when we have an even multiplicity, it comes down and just touches the 0 and goes back. When we have an odd multiplicity, it does level off a little bit. It's not like the multiplicity of 1, or the normal zeros that we've been dealing with, that it just goes straight through the point. Here it does level off, goes through the point, and then continues on the other side. Okay, so if we were to look at a case like this, here I've already factored it out. If you were to multiply it back out, we have a square, x to the first, we'd have an x cubed. That gives us an x to the 6th power if we were to multiply the whole thing out. Okay, so we actually need to account for 6 roots in the equation if we set this equal to 0. So 0 has a multiplicity of 2. 2 is just a regular 0 because the exponent's 1. And then negative 3 has a multiplicity of 3 because the x plus 3 was cubed. But you'll notice, as far as roots of the equation go, we have 2, 3, 4, 5, 6. So all 6 roots are accounted for, but we had some identical ones, so there are only 3 unique zeros. But let's take a look at what this looks like. Of course, we would plot the points at negative 3, 0, and 2 like we typically would. But now look at what's going to happen. Remember, I said this was an x to the 6th. That's an even degree. Our leading coefficient is 1 again, so that's positive. And remember, with even degree and a positive leading coefficient, we're going to go up and up. Okay, and then we have our multiplicity 3 here at negative 3. See how it levels off and goes through. And then as we approach the multiplicity of 2, 0 at 0, it comes up, touches it, and then goes back down. And then we have this other root at 2, where we have a 0 that it just passes straight through. Okay, so that's what that would look like. Alright, so those are just a couple examples of finding zeros when we can factor, and also answering one of our essential questions, which was how the multiplicity of zeros affects the graph. Okay, here's some practice problems. Hope you can try. We'll go over these on Monday. So hopefully this is helpful, and we will see you Monday.